Okay, Module 2 is focused on centroid and geometric properties. Our first practice question here is asking us about calculating the coordinates of a centroid of a plate relative to point A. So we need to give all dimensions relative to this point. The first thing that we would do is we are going to need to split this into two separate shapes, and we need to find the coordinates of the centre mass of these shapes or their centroid. Now with the triangle, we know that looking at our forming booklet, from the right hand corner the centroid is base over 3 from this side and height over 3 from this edge. Now here we need to be a little bit smart. We know this edge is 25 millimeters away because that is 80. This length, take away this length. So this is 25 to there. And we're going to take off a third of that 25. So that comes in as 25, take away 25 over 3 because it's this distance away from that edge. Our y coordinate here is just going to be the height of this triangle, which is 50, divided by 3. That's the coordinates for our triangle. The coordinates for our rectangle are going to be half of the length from this edge, but this edge is already at 25. So that's coordinates of the triangle. Coordinates of the rectangle are going to be 25, which is its offset, plus half of its width, and here it's going to be half of the height, which is 25. So we work out what these are and put it in a calculator. We would get 16.666, which is going to round to 16.7 for these. And for a square, we've got centre coordinates of 52.5 and 25. Then our next step is we would need to combine these either using the table method or the moments of area method. The table method, which we're probably familiar with, we set up a table with the shape, the area, the x, the y, the area times the x, and the area times the y. I would enter all my values, so I've got my shape, which is the triangle. Its area is going to be half times the base times the height, which is 625. Its x coordinate is 16.7. Its y coordinate is 16.7. However, in my calculator, I would leave that as 16.6 recurring for the accuracy. Then we are going to do the same for our rectangle. So we know the area of our rectangle is going to be 55 times 50, which is 2750. We know what the x coordinate is because we calculated that as 52.5 and 25. Then our next step is we need the area multiplied by the x coordinate. So that is this area times that x coordinate. And we get a large number, 110,437.5. We're going to do the same for the y coordinate. A cheat here is it's the same numbers, so it's going to be 10,437.5. We're going to do the same for the area of our rectangle times its x and times its y coordinate. So this one's going to be 2750 times 52.5, which comes at 144 0.375, and same with this one is the area times the y gives us this. Then we need to calculate the totals. So we are interested in what is the total area, what is the total area times the x, what is the total area times the y. So our total area is going to be 2750 plus 625, which is 3375. Our total of the area times the x's comes out as 154812.5, and we do the same for the y. We just want to know what our total is. So we want the total here, which is that same number plus 68750. Comes out as something like 79187.5. Then our last step is we find our x centroid. So these are the centroid equations. You do need to know these, they are not given to you. So it is the area, total area times the x's divided by the total area. So that is this big number divided by this smaller number. And we do the same for the y coordinates. It is the total of the area times the y divided by the total area. That's going to be this number that should be a point visible there, divided by 3375. We put that in the calculator and we get our y coordinate to be about 23.46. We get our x coordinate to be 45.87, and so we would write our answer nice and clearly, 45.87 comma 23.46, making sure we've got our x is the across one goes here, the y is the second one. Okay, over the page. Part B, it gives us the same plate. They've just taken the liberty of adding these forces onto here, which we note are all in kilonewtons, and removing the dimensions. It's going to ask us first to calculate the magnitude of our resultant force. The first thing that we would need to do is we are going to need to resolve, because we have a force acting at an angle. Then we are going to need to find the resultant. Then we are going to need to draw a triangle and find the magnitude. So our first step is to resolve this component at C into a horizontal component at C and a vertical component at C. Now the force at C that is horizontal is going to be, if I draw this out a bit clearer for myself, I've got 40, I've got 20k, and that is the angle. My horizontal component is going to be acting here. I've got a hypotenuse, I have got an adjacent, so it's going to be 20k times cos of 40. We are going to leave all our forces in kilonewtons because that gives us a consistent measurement, and we don't need to times everything by 1,000. It's an unnecessary step. Our y, upward component at C is involving the opposite, so we're going to do 20k size of force times sine of our angle, sine of 40. We put those both in calculator to find what they are. So 20 cos 40 comes out as 15.32k. 20 sine of 40 comes in as 12.86k. Then our second step, are going to be a bit tight of space here. We need to find the overall resultant component, so we need the resultant sideways component, we need the resultant vertical component. Our resultant horizontal component, I look and identify, I've replaced this force with a that and a that. My horizontal is 15.32, this is 12.86. And looking at this, I have got two components acting horizontally, and we are going to need to add them because they're going in the same direction. So my resultant here is going to be 15.32 plus 12, which we put in a calculator, and we find that is 27.32 kilonewtons. And because I want to draw an examiner's attention to it, I'm going to draw some attention to it, underlining it. Okay, so we've found out what this is. We also need our vertical component. Well, I've got this acting upwards and this acting downwards. This is bigger than that, so we take away this from the upwards one. So the upwards is 12.86, take away 5, comes out as 7.86 kilonewtons. That's our second step. Our third step, we're going to probably have to use a bit of space up here. Notice how we would want to show the examiner a clear step of logic. I've got my first step, my second step, my third step identified. Now, we take these two forces that we just calculated and we draw them into a triangle. So the across one is 27.32k, the upwards one is 7.86k, and we are wanting to find the resultant. This is a right angled triangle because horizontal and vertical are right angles to each other, so we can use Pythagoras here. The size of my resultant is going to be the square root of 27.32 squared plus 7.86 squared. So we put that into our calculator. And we find that the resultant force is 28.43 kilonewtons. And because this is my answer, I am going to draw attention to it. Particularly if you've gone and used more space than you're anticipating, you would make sure your answer is clearly defined. Now, the angle the resultant force makes with the horizontal, we take this triangle again with the 27.32, which we worked out, and the 7.86, and we're wanting the angle here. So we're going to need to tan minus 1 of the tangent is opposite over adjacent. So my opposite angle, opposite side, 7.86 divided by 27.32. I put that into my calculator, making sure, of course, that my calculator's got a little d for degrees, not a little r for radians. So here's our fraction, 7.86 divide 27.32, and we make sense of our answer. We've got 16.05 degrees. We take a look at our answer and we just reality check it. This is further across than it is up, so it's going to be less than 45 degrees. that's less than 45 degrees, we're probably along the right lines. If we got something bigger than 45 degrees, it means we've got our fraction the wrong way around and we need to swap them round. Right, the moment due to moment at point C due to forces acting on the plate. Here we need to know that a moment is a force times the perpendicular distance, and we're also going to need to know our dimensions. Now our dimensions, because they're going to try and trick us, they gave us on the last page. They're going to see if we could remember them or just look back. So we've got 80 millimeters is from A to D and 50 millimeters from D to C. So this side length here is 50 millimeters and this length here is 80 millimeters. Now, whilst you could change these into meters and these into newtons, changing these into meters would give you a -3 conversion factor. These would give you 10 to the 3 conversion factor. And because we times them together, it's going to cancel, so it doesn't matter. Now, the moment at point C is the turning force exerted by about this point. The forces that have got a turning moment, if I put my finger there and I push in the direction of the forces, any force applied at C is not going to have a moment. However, this one at D is going to have a moment that is anti-clockwise, and A is going to have a moment that is anti-clockwise because it makes it spin anti-clockwise when I push in the direction of the force. So the total moment is going to be size of force 12 kilonewtons times 50 millimeters plus 5 kilonewtons times 80 millimeters. I put in here a conversion. I'm going to put the conversion for those. We see that 10 to the 3 is the K times 50 times 10 to the -3 plus 5 times 10 to the 3 times 80 times 10 to the -3. It's gone off the page. We can see that here, that is the size of a force times the perpendicular distance, size of force times perpendicular distance. These conversion factors here will cancel. So I'm basically doing 12 times 50 plus 5 times 80, which I'm going to put in my calculator. And we get an answer of 1000 Newton meters. Or we could change that into 1 kilonewton meter. Either would be relevant here. Why have we added them? Just a reminder, because this would make it spin anti-clockwise, this would make it spin anti-clockwise. They go in the same direction, so we add them. Okay, question 2 is a good recap. And question 2 is asking us to calculate the cross-sectional area of the beam. Now we would be sensible and split this into 3 shapes. I've got the bottom, the top and the middle section. My middle section, I want the area. Now this is only 2 marks. We need to see, for 1 mark that seems quite easy. We need to read the whole question. It mentions up here that dimensions are in millimeters. It mentions here that the units must be in meters squared. So we are going to first need to find our area in millimeters squared, and then we need to convert, or we convert first. Converting first will give us lots of zeros to deal with. It might be easy to convert second. So my first step, area. My second step is convert units. The area in millimeters squared. I've got this bottom one, which is 102 times 7, because its thickness is 7. I've got the middle one, which is 240 times 6, plus I've got this top one, and it is 102 times 7. I put that in my calculator. and we see that it is 2868 millimeters squared. Then I need to convert from millimeters squared into meters squared. You need to know either how to get your conversion factor or remember. The remembering one is between this to this is a factor of 10 to the 6. And because I'm going from many small ones to one big one, I divide. So here, convert the units. Area in meters squared. Make it clear what you are calculating at all times. I've got 2868 divided by a million. I'm going to put it into calculator as 10 to the 6 because then I don't miss how many zeros I put in and it's just shorter. So I've got 2868 over 1 times 10 to the 6. And we end up with 2.868 times 10 to the minus 3 meters squared. And I'm going to make it clear what my answer is. Then the next step, we want to calculate the mass of the beam. It gives us a length, it gives us a density. We need to know how to calculate the volume first. We then need to calculate the mass. Our volume we get because a volume is a cross-sectional area multiplied by the length. These need to be in the same units. We've just found this in meters squared. We've got our length in meters, so we're all good. So our volume is the cross-sectional area we just calculated times 12, which is the length, and we get that in meters cubed. 0.034416. Then we need to calculate our mass. Now our mass is going to be the volume multiplied by the density. So our volume was 0.034416. Our density is 8,000. We multiply those together. We end up with 275.328 kilograms, which we are going to do some rounding on because that's a ridiculous amount of precision to claim. So let's say 275 kilograms. And then we reality check. Would a steel beam that's about 10 centimeters by about a foot I-beam that's 12 meters long, is it likely to weigh about 275 kilograms? Yes. Is it likely to weigh 27 kilograms? No. So if you get up with 27 kilograms, you have got a conversion error somewhere, and that is a light bulb to go and check. Right, question 3. It's wanting a centroid. We have done centroids before. This is the same steps as number 1, apart from you're going to have to split it into 3 shapes. I would suggest these 3 because then you don't have to deal with any X offsets. You've only got Y offsets to deal with. And then question 4 is extra practice on question 2. The one little bit that you would need is you need to know how to go from weight in newtons, how to get that from mass. That is some GCSE science knowledge which will become in handy, which is the weight is equal to your mass in kilograms times the strength of gravity, which is 9.8 newtons for each kilogram. Do check on the front of your book, especially if you take physics, because the level of precision you quote gravitational field strength to changes. And question 5. First thing, it's a semicircle. You want to check your formula booklet because it has got the centroid position for a semicircle. Part B requires us to apply some knowledge here. We know where the centre of this would be because it's a rectangle, it's in the middle. So it's going to be 200 from this side and 75 from the bottom because that is half of the width and half of the height. When we hang something from a corner, corner A, we end up with the centre of mass directly below the point we hang it from. So if you can imagine, if you hung that up here, we are wanting the angle it makes from the vertical, the side A to B. So we could rotate this so that we know which angle we're looking at. That is this side here. It's wanting that angle. We would need to know a couple of things. We would need to know how far this is. We can always turn it into a triangle, and we see that this is halfway along. So this distance here would be 75 millimeters. This distance here would be 200 millimeters. We know how to find the angle there. So I would, for sake of making it easier on myself, I would draw this out somewhat. That is A to B. I've got a right angle, I've got 75 degrees, and I've got 200. I want this angle here. So that is my angle, and I've got my label at my sides. I've got a hypotenuse, I have got an opposite, and I've got an adjacent. I know that tan is opposite over adjacent, so I'm going to do tan minus 1 of the opposite, which is 200 divided by 7.5. I'm going to check that my calculator is in degrees and not radians. And I'm going to type in tan to the minus 1. And we find that it is 69.4 degrees. And then we reality check it. Here we can see that this is quite a big angle, bigger than 45 degrees. Is my answer bigger than 45 degrees? It's in the right region. Okay, that's pretty much it for the Module 2 questions.